Now we are gonna talk about mass spectroscopy, prepared by Abdulrahman Osama Mahmoud Hussein, Ahmed Mohammed Jaheen Gharib, Fatma Mohammed Hassan Mohammed, Hams Ahmed Subhi Mohammed, كورولوس عماد عدل عطية، كورولوس فيكتور توادرس حنا، سما ربيع إمام الهم، وليد فوزي حليم عبيد. Under the supervision of Prof.dr.Samy Abu El-Wafa. Introduction to Mass Spectrometry. Mass spectrometry is an analytical technique which is the most accurate method for determining the molecular mass, molecular formula of the compound and its elemental composition based on the different mass to charge ratio of gases ions. Mass spectrometry is most generally utilized in organic chemistry, but at the same time is extremely valuable for the analysis of inorganic compounds. Mass spectrometry is also extremely sensitive. Femtomole quantities can be detected. Determination of molecular formula by mass spectroscopy. Main information given in mass spectroscopy analysis: molecular weight, number of specific elements based on isotope peaks, molecular formula with high resolution mass spectrometry, reproducible fragment patterns to get clues about functional groups and or arrangement of components or to confirm compound identity. How does mass spectrometry work? Molecules in a sample in the gaseous phase, then an electron beam bombards the vapors, which convert the vapors to ions and broken up into many fragments. Because mass spectrometry measures the mass of charged particles, only ions will be detected, and the neutral molecules will not be seen. The mass spectrum is a plot M over Z values of the various ions, x-axis which is the parent ion as well fragment ions, y-axis which is relative abundances. In the mass spectrum, the peak of the extreme right, which particle of the highest mass corresponds to the molecular mass of the original molecule. In case of straight chain hydrocarbons, the abundance of the parent peak is fair and it's also give M+1 peak. Mass spectrometry for inorganic chemistry. Information we can get. First, M plus ion, the parent ion peak. If observable, gives the molecular weight of compound if Z equals 1. Second, isotope pattern. Characteristics of some elements such as some halides, chlorine and bromine. Also many transitions metals like platinum and mercury. Isotopers defined as two compounds differ only by isotopic mass of one or more atoms. Fragmentation patterns. Often fragments of the M plus ion fall off. Observe this fragmentation at lower masses. Often see the loss of ligands one at a time. FeCO by 5, M plus equal 196 AMU. Now we can see in this slide a figure that shows the composition of mass spectroscope. Spectroscope consists of 5 main components, which are a high vacuum system, a sample handling system that allows the sample to be investigated and introduced, an ion source that produces a charged particle beam characteristic of the sample, an analyzer that allows the beam to be divided into its constituent parts, and finally, a detector or receiver that allows the separated ion beams to be observed or collected. In this slide we can see the most common fragment that we can observe in mass spectrometry. Now let's talk about isotope ratio measurements. First, compounds that containing chlorine atom. The molecular ion peaks M plus and M plus 2 each contain one chlorine atom, but the chlorine can be either of the two chlorine isotopes, Cl35 and Cl37. The molecular ion containing the Cl35 isotope has a relative formula mass of 78. The one containing Cl37 has a relative formula of 80. Hence, the two lines at M over Z equals 79 and M over Z equals 80. Notice that the peak heights are in the ratio of 3 to 1. That reflects the fact that chlorine contains 3 times as much of the Cl35 isotope as the Cl37 one. Second, compounds that containing bromine atom. Bromine has two isotopes, Br79 and Br81, in an approximately 1:1 ratio, 50.5 to 49.5, if you want to be fuzzy. That means that a compound containing one bromine atom will have two in the molecular ion region, depending on which bromine isotope the molecular ion contains. Unlike compounds containing chlorine, those two peaks will be very similar in height. Finally, we are going to talk about the benefits of mass spectrometry that we can obtain. First, identification of compounds. Mass spectrometry is widely used to identify unknown compounds in a sample. The unique mass-to-charge ratio M over Z of ions generated allows for precise identification. Second, quantitative analysis. MS is employed for quantitative analysis, determining the concentration of specific compounds in a sample, isotope dilution, and multiple reaction monitoring, MRM, are common techniques for accurate quantification. Thank you for watching.
Then we're gonna talk about mass spectrometer. Mass spectrometer is an analytical tool used for measuring the ratio of mass to charge. When we put the sample in the device, the molecules of the sample pass through 3 stages. The first stage is ion formation, the second stage is ion separation, the third stage is ion detection. We will show to you in detail how it works in the next few minutes. The journey of the molecules begins from the sample inlet. The molecules flow at low pressure in a steady stream by a pinhole called molecular leak. Then the molecules convert from liquid or solid state to gaseous state by the action of the heating coil in the sample vaporization chamber. Then the molecules go to the second chamber, which is called ionization chamber. Molecules are ionized and broken up into many fragments by bombardment with a stream of electrons by the electron gun. Some of the fragments are positive ions. Each one has its particular ratio of mass to charge. Then the ions go to the third chamber, called ion acceleration chamber. The ions are accelerated to have the same kinetic energy, leaving the third chamber, the acceleration chamber, going to the fourth chamber, which called mass analyzer. Ions are exposed to a magnetic and electric field in the fourth chamber that cause deflection. The deflection of ions depends on two factors. The first factor is the mass. The lighter the mass, the more they are deflected. The heavier the mass, the less they are deflected. It have inverse relationship. The second factor is the positive charge. The more the positive charge, the more will be deflected, and the less the positive charge, the less will be deflected. It have direct relationship. Then the ions goes to the detector. The beam of ion passing through the mass analyzer is detected by a detector on the basis of the mass to charge ratio.
Electron impact ionization, chemical ionization, electron spray ionization, electron impact ionization. A stream of electrons generated by using a heated filament and the other end of chamber has plus charge. Electron which accelerated electrons that have energy about 70 eV and wavelengths about 0.14 nanometer, which equivalent to the dimension of the chemical bond. When electron hits the molecule, it breaks the bond and electron release and give ion. The working of the device. The sample firstly vaporized and introduced to the chamber through inlet. The high energy electrons collide with molecules and break into small fragments, so energy released. The fragmented molecules will have a charge. To analyze these fragments, there is a repeller. Electrode will have a charge and repel charged ion and accelerate them to analyzer. Now we will talk about chemical ionization. Ionization here we will use methane ion or ammonium ion because they large in size compared to electrons, so the probability of ionization increase even more. NH4 collide to the sample and break the chemical bond. Electrons are released during breaking the bond. Charged ions are obtained and go to the analyzer. Electron spray ionization. Sample can mix it with methanol, acetic acid, acetonitrile, ammonium hydroxide, plus water 1:1 ratio. Depending pH of solution, the sample can either have positive or negative charged ion. If acidic will be positive, if alkaline will be negative, the charged molecule pass through a ring to create an aerosol. This process called nebulization. Due to vacuum inside chamber, the solvent molecule evaporate and leave charged molecule to enter analyzer. To increase the rate of vaporization, apply potential about 3000 eV at the end of the ring. It makes the solvent molecule electrically charged as the sample, and solvent molecule have the same charge. The rate of vaporization increase. Now we will take about analyzer. The charged ion which came from the three techniques enter the analyzer and allow to pass through. Gold magnet, the charged particle in the magnetic field, force which equal to QVB. The separation of ion occur after separation. It pass through curve way and detected by detector and information obtained on computer.
In the end, we are talking about the application of mass spectrometry. It certainly has great importance in many fields, but we will talk about the most important application, which is monazite. Let us ask a question: how do we apply mass spectrometry in monazite is of great importance. How? We use mass spectrometry in separation of pure elements such as lanthanide in monazite ore. First we ask, what is the monazite and what it look like? Look at this picture. This is the monazite stone, but isn't like any ordinary stone. It's very important stone. This rock had a reddish brown appearance and slightly radioactive element. And is a dense phosphate mineral which is about 5 to 5.5 as dense as water. This is some of its physical property. Now we're talking about the chemical formula of monazite. This contains two portions. The first and left contains some very important elements: cerium, gadolinium, lanthanum, neodymium, samarium, and thorium. The second portion in right, PO4, that is phosphate group. Note that the overall importance of this rock lie in the first part or this first section. Why? Because this element called rare earth element, except thorium. We will discuss the importance of this element later. Then what is the importance of this rare earth element? This rare earth element used in wide variety of today's modern technology. Let we know like what? In smartphones, digital camera, computer hard disk, fluorescent and LED lights, flat screen television, and in clean energy. Another example of application of mass spectroscopy is chalcogenides. This is material are used for a wide range of application in flexible electronic. It's formed principally from chalcogen element atom, for example, sulfur, selenium, chlorine. This makes the device cheaper than before. Now we will discuss that mass spectrometry can be employed in the separation of pure elements from monazite ore, including lanthanoid. This process typically involves several steps. The first step is sample preparation. Monazite ore is first processed to obtain a representative sample. This involves crushing the ore and possibly using chemical treatments to break down the matrix. The second step is ionization. In this step, various ionization techniques can be employed, such as electron impact ionization or electrospray ionization. The sample in this step is ionized to create charged particles. Step 3. Acceleration and deflection. The ions are accelerated and then deflected by an electric or magnetic field based on their mass to charge ratio, m over z. This step separated ions based on their mass, allowing for the isolation for specific elements. Step 4. Deflection only. The separated ions are then detected and their abundance is measured. This data is used to identify and quantify the different elements present in the sample. Step 5. Isotope ratio analysis. Lanthanoids often have multiple isotopes with different masses. Mass spectrometry can be used to analyze the isotopic composition of each element, providing additional information for their identification. Step 6. Data analysis. The collected data is analyzed to determine the concentrations of individual lanthanoids in the monazite ore. This allows for the calculation of the purity of each element. Overall, mass spectrometry provides a powerful tool for the precise analysis and separation of elements in complex mixture like monazite ore.